Hi, Kate Meredith here with Global Systems Science Global Climate Change Unit. In this video, we're going to be taking a look at Investigation 2.3, Why do some molecules absorb infrared energy? And in this investigation, students are going to use models to answer this question. And they're going to build 4 different models representing some of the gases that we find in our atmosphere. And they're going to do an input of energy, which is going to be their hand, and they're going to shake each one of these molecules. And they're going to discover that as they change the rate at which they input the energy, or shake their hand, that the molecules will respond differently. And some molecules will respond at a slow rate of shaking, which corresponds to our understanding of infrared light, having a longer wavelength and lower energy. And some molecules require a lot of shaking and some don't respond at all. Now, the tricky thing about this investigation is you don't want to figure out how to build molecules on your prep period. So I've tried to take some of the guesswork out of it for you by looking for the least expensive way to build these molecules and have the least amount of materials and the greatest chance for success. So what I did was I tried a lot of different things, but in the end what I decided would work the best was plain old pipe cleaners and styrofoam balls. So pipe cleaners, pick 2 different colors just because it's easier to see how you twist them together, because you will need to twist them together to get the right kind of combination of springiness and stiffness. And styrofoam balls, I found a particular kind that were smooth styrofoam balls, and what I liked about these was they held really well up to, they're a little stiffer, they have a smooth coating, a little harder to get the pipe cleaner poked in, but they held up really well to a lot of shaking. They also have a little bit more mass to them, which was really helpful in this experiment. So they're 1.5-inch styrofoam balls, and these smooth ones also have a line around them where they were formed, which is really helpful for orienting where you're going to put, how you're going to connect these styrofoam pieces. So first thing you do is you take just a regular 2 pipe cleaners, and you're going to be twisting a bunch of these together. I suggest you do them all at the same time because it's kind of a zen thing. You want to get 4 twists in here and pinch them together and just give them 4 turns. And when you do this, you're going to find that if you do it right, all of your colors will line up. That's how you know you have this correct. And again, I try and point out to the students that the reason why we do this is we want a nice model. We want everything as much as we can to stay the same. Another thing that I needed in this model was when I made the larger methane molecule, I thought it was much easier to get it poked into a regular 1.5-inch styrofoam ball, and it was just a lot easier to insert the pipe cleaners where I wanted them on these balls. So 2 different kinds. Also, when you want to poke in your styrofoam balls into these heavy-duty ones, I suggest you do a push pin first, make your initial hole, and then just wiggle it around a little bit so that the hole is large enough to insert the pipe cleaner. So once you have a number of these, the pipe cleaners twisted, you can go about constructing your balls, your molecules. And so you're going to need, for your nitrogen, you're going to cut, these guys have the strong bonds, and for the strong bonds I found that we needed 12 centimeters worth of pipe cleaner inserted on each end of the balls. Another nice thing about these smooth balls that I found was they already had a hole, a large hole at one end, and I could easily get 3 pipe cleaners for the nitrogen pushed in and 2 in for the oxygen molecule. And again, you've got these twisted, you're going to just lay them out, measure them, cut them with a pair of wire cutters. You can use scissors or just bend them a lot, but it really is a lot more efficient if you can get a hold of some wire cutters. So 12 centimeters for these strong bonds. Okay, so we made those a little shorter and made things a little stiffer. You can talk to your students about that. And 15 centimeters for the weak bonds. And the nice thing about 15 is you can get it easily out of a 30 centimeter pipe cleaner. You can get all the bonds that you need. Then on the carbon dioxide molecule, you also have 4 weak bonds, so another 15 centimeter lengths. You need 4 of those. Push those in and get them centered. A nice extension for those kids to get done fast is actually have them orient these so that they're on as a tetrahedron, and there's some diagrams in the book showing you how to do that. They can experiment around with that and see if that changes the resonance. The nice thing about, I didn't worry about using a different kind of styrofoam ball for the center because you're going to hold this one by the center. And you really want to check around when they have this done correctly. They should be able to shake them and find the resonant frequency for these different molecules. And the first 2 are fairly easy. You're going to hold them by the center. I strongly recommend you actually find the center of gravity for these last 2, or it's going to be a little bit more difficult to feel the difference. They can do these 2 at the same time because the oxygen molecule, you can actually get it going, but you have to go very fast, and you can feel a difference between that one and the nitrogen, which you can shake and shake all day, and as fast as you can, we'll see which one of your students can actually manage that one to get going, but I have not been successful. So at these particular configurations, 4 twists between 2 pipe cleaners together, making your bonds. You have 12 centimeters for your strong bonds, and the number that's called for in the book, 3 for your nitrogen, 2 for your oxygen. Your carbon dioxide have weaker bonds, 15 centimeters, construct those with 2 bonds between them, and then your finally weak bonds at 15 centimeter pipe cleaner lengths for your methane. And that's really all there is to it. This is a very important investigation because it sets students up to understand that there are models used to understand things in global climate change, and that models have their strengths and their weaknesses, and this will come up again in the controversy and consequences unit. And it also shows students that we are actually working with some scientific known facts on how molecules behave, how they absorb energy, and that's the foundation for all of our decision making scientifically when it comes to global climate change. So good luck, have fun, and do let us know if you find another inexpensive, easy way to make this investigation even better. Thanks a lot.